So the topic of set theory is, it's a mathematical concept, but comes up very much in life in general, but also just in computer science. So, so a definition of a set would be a collection of items, right? So yeah, again, it comes up in computer science and mathematics. Set is a well-defined collection of items, and we're going to typically denote them with capital letters, like A, B, X, and Y. The elements or the members of the set will use small letters, like small x and small y, to represent them. So, so we could define two sets as being equivalent to each other or not equivalent to each other. If two sets have the same exact members, they're considered equivalent to each other. Otherwise, they're considered not equivalent. So we use equal signs and non-equal signs in those cases. Okay. So we can define sets by, there's two popular ways of defining sets. One is just list out every item in the set. So for example, we could say set A is A, E, I, O, and U. One thing we could do. This is an example of a finite set. So it has a finite number of members. We could also say, we could list them out as all their items by saying 1, followed by 3, followed by 5, and then dot, 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 meaning continue that pattern, which would be 7, 9, all the way off to infinity. So that's an example of an infinite size set, infinitely many numbers. And another popular way of representing sets is to say, to describe the properties of the set. So for example, set C could be all x's such that, two dots means such that, x is a letter in the alphabet, and in addition to that, x is a vowel. Okay, and then set D would be all x's such that x is an integer and x is greater than 0 and x is odd.
So it's kind of like a for loop.
Well, yeah, so basically, yeah, so in the end, really, set A and set C are the same thing.
Mm-hmm.
I listed out every vowel, and then I kind of described vowels. I said, and I kind of did it as sets and subsets. I'm basically saying X is in the set of all letters. Then you take that set and make a subset out of it, and only the ones that are vowels. So I'm like taking a subset of the set. And in this case, I'm kind of doing the same thing. I'm saying X is an integer. So that's everything from negative infinity, all integers from negative infinity all the way to positive infinity. Then I'm saying only the ones that are greater than 0. So I just knocked out, I made a smaller subset. Still infinitely long. And then I said only the ones that are odd, so I knocked out all the even ones. So really, D and B are the same thing. This and this is two ways of saying the same set. Okay. So, suppose, for example, we have these three finite sets. Set A is 1, 3, and 5. Set B is 1, 2, and 3. And set C is 1 and 3. So as far as like subsets are concerned, we could ask the question, is A a subset of B? A would be a subset of B if every member of A also appears in B. B may have more stuff, but if every member of A appears in B, then it would be a subset. So the answer to this would be no, because A has a 5 and B does not. So A is not a subset of B. And the notation would be this thing. You're saying A is a subset of B. Then we could ask the question, is C a subset of B? And we could write it the other way around. We could say B is a superset of C. And the answer to that one would be yes, because 1 and 3 are both in B. Right, so 1 and 3 are both in B. Then is C contained? Contained is just another way of saying is a subset of. Is C contained by A? And the answer is yes, 1 and 3 are both in set A. And then another way of saying it is, does A contain B? Is A a subset? That's like the first question being repeated. And B has a 2. So yeah, so is A contained in B? And it's no, because B has a 2. And it should be capital A. A does not. Okay. Okay, and then there's some common sets that just show up in mathematics. So they kind of, it's understood when you see these letters to represent the set name, it means these sets. So over your mathematical career, you might see these letters. It's like N being the set of all positive integers, the natural numbers. Z being the set of all integers, negative, from negative infinity to positive infinity. Q is the set of all rational numbers. So that's any number that can be expressed as a number divided by another number, which is a subset of all real numbers. R is the set of all real numbers, and C would be the set of all complex numbers. So it's just popular mathematical notation. If you see these letters, it means that set of numbers. That's more of a math thing than anything else. Okay, then for every possible set of members, items that could be members or not members, there's a set called the universal set, which means it's the collection of all possible members. And there's also a special set called the empty set. That's the set that has no members to it. So for example, R, all rational numbers, is the universal set for all rational numbers. That's every possible rational number. And another example could be all members of Facebook, like whatever today's date is, all the people who are members of Facebook, that is the universal set for Facebook members. So set theory comes up like in computer science, for example, you might be a member of Facebook, and you have a set of friends on Facebook. And then, you know, sometimes you could log into Facebook and it says, you may know these people. And typically what they're doing is they're taking the set of all your friends and then saying for each friend of yours, they want to see the set of their friends. And then they combine all those sets together. And then they delete out all the people you already are friends with and say, you may know these people. So it's kind of like friends of friends. So they're compiling a bunch of sets on top of each other. Okay, so sets could overlap. Like for example, you could have a friend on Facebook, you could have two friends on Facebook, and they're both friends with the same person. So there could be some overlap in sets. So it's possible, it's useful to use what they call a Venn diagram for sets. So for example, if we had this set, these are all the set of, let's say, red items. This circle represents all the red items. This one represents all the blue items. This one represents all the green items. And then there are members who are both in the red set and the blue set. And they show up in here, this area, this kind of football-shaped area, the purple and the white combined. Those are members of both the red set and the blue set. And same thing with the members of both the green and the blue set show up in this light blue section and this white section. And red and green overlap with the yellow and the white sections. So the red section is comprised of the red part, the pink part. Does it look pink or purple?
Purple.
All right, so it should be purple. Maybe I'll change the slide then. The white section and the yellow section. That would be the red set, which could also have members that are somewhere else. So this could be like one of your friends, and then this is another friend, and then this is a person who's a friend of both of those friends on Facebook like that. So we could use union and intersection symbols. We could say that the intersection of the red section and the green section, you're taking the red section and the green section, the intersection, which is members who belong to both sets, would be the yellow section and the white section. And then we could say what members are in the red section and must also be in the blue section and also in the green section, and that would be just this section in the middle. Only members in here are members of all three sets. And you could do unions. You could say all of this. So this, the red, blue, and the green would be everybody who's in anywhere in this area would be considered in red or blue or green. And we could also do subtraction. We could say the red section minus the blue section. So the red section is this entire circle, and the blue section is this circle. So the red minus blue would be what's red and the yellow part, but not including the white part, because white members are also in the blue set. Okay. Okay, and then there's some laws of, the algebra of sets. So the idempotent law is the one that says if you take a set A and you union it with all the members of A, which ones do they both have in common, you would get A. doesn't generate any new members, doesn't lose any members. If you say, I only want the members that are in A and must also be in A, that would still be A again. The associative law is saying that if you were to take the union of A and B, do this operation first, and then take this set and union it with the set C, that would be the same as doing B and C, getting all the members they have in common, and then adding all the ones that A also contributes. Same thing's true with the intersection operators. The commutative law is just saying left side and right side don't matter. If you took a set A and then added every member who's in B that's not already in A, that's the same as taking the set B and adding all the members that are in A but not in B. And same thing's true with the intersection operator. The distributive law is saying if you have an operation, if you say A union B intersection of C, you could break these apart and say it's A union B intersecting with A union C. And that kind of shows up in this picture. If you took, let's say, the red and the blue, if you wanted to take the intersection of B and C, let's say the intersection of B and C would be here. Let's say this is A, B, and C. This is the intersection of B, B, and C, and then you want to union that with A. That would be the same as taking A and unioning it with B, and taking A and unioning it with C, and then taking the intersection of those two. Okay. Then identity ones would be when you multiply, you say A in union with an empty set will produce A. A intersected with the empty set will produce an empty set. A union with the universal set would be everything. You're taking everything that's an A and then you're taking every member possible. You would get every member possible. And if you had every member of A intersected with the universal set, you'd get back with A. Because they have to appear in both sets. And this has every member, and this has only the A members. That would give A. And then there's the idea of the complement. The complement of any set is everything that's outside of the set. So the empty set complement is the universal set. The empty set has no members, and the universal set has every member. So they're complements of each other. The complement of the universal set is the empty set. If you took a set A and took its complement, which is basically saying everyone who's not an A, and then took the complement of that, you're back to everyone who is in A. And if you union A with the complement of A is every member of A complement is every member who's not in A, put it all together, you get every possible member. And then famous De Morgan's theorem is if you took A union B, so what A and B have in common, let's say this is A and this is B. So everything in both of these circles together. If you took the complement of that, everything outside of it, that would be the same as everything outside of A intersecting with everything outside of B. Those two ways of expressing De Morgan's law. De Morgan's law of sets. Okay, so then, so we can talk about finite sets. Finite set contains exactly m elements where m is a non-negative integer. So for example, the empty set is a finite set. Another example would be all the letters of the alphabet is a finite set. 2, 4, 6, 8, and so on is an infinite set. And all Facebook users is the finite universal set for Facebook. Every possible member of Facebook has to be in the set of all possible ones. Okay, so if we wanted to count the number of elements in sets, we can only count them if they're finite. If they're infinite, then we know they have infinitely many. So it's possible, depending on the author, to say n of a set or pound of a set, means the number of members in the set. So that's the number of elements that are in set A. So if you wanted to know how many members are in set A union set B, so that would be if you took all the members of set A and you took all the members of set B, but some of them may overlap, so you don't want to count them twice. So what would that be? If it's possible they could overlap, what would it then be?
You'd have to minus that part out.
You'd have to, yeah, so really what we're doing is we're saying, if we said the number that's in A plus the number that's in B, it's possible we counted some members twice if they happen to be in both sets. So then we would just subtract one copy of that, subtract the number that is in both, and we get the correct number. And if you had more sets than two, the principle just continues. So if you want to know how many are in the red set, the blue set, and the green set, it would be the number in the red set, plus the number in the blue set, plus the number in the green set. Now if we did that, that's this thing, we added everyone here, and everyone here, and everyone here. So everything in these weird football-shaped things got added twice. So now if we subtract them, if we subtract one copy of each out, the number that's in the union of red and blue, and the union of red and green, and the union of blue and green, we subtract one copy of each out, then we subtracted this piece, that should be a plus sign, sorry. This piece, we subtracted that out 3 times. Well, we only should have subtracted it out 2 times. So this should actually be a plus sign. Let me change that. Oh, you know what, I'll change that after class, so. Okay. Right, so what we'd be doing is we'd be adding these 3 together. So this piece, and this piece got added in twice, and this piece in the middle got added in 3 times. So we want to subtract out this whole piece, this whole piece, and this whole piece, but now we subtracted this thing out completely, so we add 1 back. So yeah, let me change that now. So this should be plus. Okay. Okay, right, like that. Okay, and then if A and B are disjoint sets, if they're 2 separate sets, there's no overlap, then this would be 0, right? The number that is in both would be 0, so we can get rid of that. So if they're disjoint, then we can say that. Okay, then the idea of classes of sets, which is just another fancy way of saying sets of sets. We could have a set that has the elements 1, 2, 3, and 4. And we could let A be the class of all subsets of S containing exactly 3 members. So that's really a set of sets that have the original set as members. So it would be the set of 1, 2, 3, and 1, 2, 4, and 1, 3, 4, and 2, 3, 4. That's all the possible sets that have 3 elements of the original set. So this is really, A is really a set of subsets of this set. So it's sets of subsets, but they call them classes of sets. And we say let B be the class of subsets of S containing a 2 plus 2 other numbers. So that would really be a 2 plus 2 other numbers means it must have 3 members in it. So it would really be a subset of this set. And we'd only take the ones that have a 2 in it. So 1, 2, 3, 1, 2, 4, 1, 2, 4, and 2, 3, 4. Okay, so then there's the idea of the power set of a set. So if we had a set, let's say S1, which contains 1 member, the number 1, the power set is all possible subsets we can make of it, every possible subset. So there's always the empty set. You could always take members and say, all right, I'm not going to include any of them. I'm going to make a subset with the empty set. And the only other thing we could do is the set 1. These are really the only 2 possible subsets you could make from this set. Now suppose we added an additional item, 1 and 2. We added a 2 to this set. So now we have 2 elements. So what are all the possible subsets we can make? Well, we can make obviously these 2, which we had before. So it's the empty set and 1. And now, what other sets can we introducing a 2 could we make? Well, we could add a 2 to the empty set, which gets us the set of 2 by itself. And we can add a 2 to the set of 1 and make the set 1 and 2. So we don't want like 2 and 1 and 1 and 2 are considered the same set. Order doesn't matter with sets. So now suppose we added a 3rd element, number 3. Well, we could take these 4 sets These are 4 subsets we can make out of these 3. And then anything that introducing a 3 could be added. And really what we do is just take the previous set of sets and put a 3 in everywhere. Put a 3 on this one, put a 3 on this, put a 3 on this, and put a 3 in here. So we would end up with the first 4 we had before, the empty set, 1, 2, and 1 and 2 combined. And now all the sets that 3 introduces. 3, 1 and 3, 2 and 3, and 1, 2 and 3. So every time we add a new element to our original set, we double the number of elements in the power set. So the number of members in the power set would be 2 to the number of members in the set. So if you have 3 elements, you could make 8 possible subsets of that up. Okay. Okay. So our whole lives we've always been using set theory, and our mind puts things into sets, and then we rule what's in one set and not in another set, and so on. And suppose in an artificial intelligence, as you go through your computer science degree, you might take an artificial intelligence class. And what you could do with a fact-based system or a rule-based system is, if you know a certain set of facts, could you then take those facts and conclude new facts? And you don't want to conclude something that may not be true. You only want to conclude things that are definitely true. So suppose, for example, you had 2 facts. One fact is everything in the garage is useful. And you have another fact, fishing poles without hooks are useless. Now, could you draw the conclusion everything in the garage has hooks? And what would be like your answer?
Like if you had a saw, the saw doesn't have a hook on it, but you could say that all fishing poles, because everything in there is useless, all the fishing poles must have hooks.
Okay, so yeah, so you gave an example of a saw, which has no hooks, but is still useful and doesn't violate these facts. Everything in the garage is useful, and fishing poles without hooks are useless. Yeah, so that's an item. So what you really did, like in a way, does it kind of seem like you was thinking of sets, putting stuff into sets and then asking yourself, is there something that could be a member of one set but not appear in the other set? So like in this example, what are the sets and what are the members of the sets?
Everything would be,
Everything,
garage would be a set right now.
the garage?
No, everything would be a set, and then the garage would be,
One set would be everything in the garage.
Right, that's one set, everything in the garage,
And then all fishing poles would be another set. And then you would have
then that would
poles
break into 2 sets.
that
the
are
ones
either
that have
hooks
and
or
don't
no
have
hooks.
hooks. Also, anything that's useful would be a set. So it looks like, yeah, so if you think it from the point of views of sets, there's 2 kinds of items. Useful items and their complement, useless items. Right? So useless items is a set, useful items are a set, and actually one's the complement of the other. There's no such thing as something that's not useful and not useless. So I guess, yeah, we'll consider those complements of each other. And then anything that's in the garage is a set, and it is a proper subset of anything that's useful by this first fact. Anything in the garage is useful means everything in the garage is a subset of useful stuff. So, everything in the garage is a subset of everything that's useful. Now, fishing poles without hooks is one member of the complement of useful, the useless section. So with those 2 facts, can there be an item that makes this not true? So just kind of looking at it from a set theory point of view, you have the universal set, every item. Then you have A, which is all the useful items. That's in the blue and the green section. The white section is all the useless items. And then this area is the stuff that's in the garage. So now the question is, so if B is everything in the garage and A is everything that is useful, then everything in the garage is a subset of what's useful. So B is a subset of A. And then everything in the universal set minus A is all the stuff that's the A's complement. That's all the stuff that's useless. And then fishing poles with no hooks are a subset of what's useless. So all fishing poles without hooks are out here. There's none of them over here. And that would be a disjoint set. That would be a set out here, and a set of all stuff in the garage are disjoint sets. So everything in the garage has hooks would not be true. Of course, they're disjoint sets. If they could have overlapped, well, I wouldn't say everything, but then some things could be in the garage that have hooks, would be possible. So in a way, I'm just, just kind of going over the idea that you could take facts, and what these facts, if they use the word every or some, are really building up members of a set. How you doing? You looking for a discrete math? Oh, okay. Okay. So suppose we have these three facts. So I guess someone who's double majoring in computer science and poetry came up with this example. Suppose these were three facts. Every poet is happy. Every programmer is wealthy. And no one is happy and wealthy. So that what this is getting at is you're building sets, you have members of sets, can the sets overlap or not overlap, and then if they can overlap, you can draw conclusions on that. So, two conclusions are possibly being considered. No poet is wealthy, all programmers are not happy. Now, are these always true?
In real life or in this?
No, in this thing.
Oh.
Yeah, like I said, whoever came up with this was probably a double major and
Yeah, in this it would have to be.
switched from one major to the other, yeah.
These
So,
would be facts. They would be true, right? No
does anyone think one of these may be? If so, for something to be true, it has to be true in every case. For it to be false, all you have to do is show one case where it's not true. Like I know there's one guy who is not a poet, but no poet as well, is a poet and wealthy. That would be a contradiction, then it would be false. So yeah, I guess these conclusions, are they 100% true?
Based on the facts given, they
Yes.
would be.
They look like they would be? Okay, good. So you guys are all you're doing set theory. You'd have to be doing this using set theory, but, so in this case, yeah, they would both end up being true. And the reason is we would have two sets, happy people and wealthy people. And this third set is saying those two sets are disjoint. No one is happy and wealthy. So you can have happy and you can have wealthy. And then poets are a subset of happy. So poets are inside of here. Programmers are inside of here. And they're disjoint. So then the question is, no poet is wealthy. So to be a poet and be wealthy, you'd have to be a poet which is in here, and you'd have to also be in here, and you can't.
So could you, sorry to interrupt, could you also draw the conclusion that no poets are also programmers?
Right, that's another side conclusion.
Okay.
Right. So, right, because all poets are in here, and all programmers are in here. So there's no such thing as a person who's a poet and a programmer, based on these facts. Right, so in your head was something like this going on? Like, well, these people are over here, and these people are, so we always use set theory in a lot of our thinking, and it's just kind of good to spell it out. So in this case, I only replaced one word. I just said every on the last example, now I'm saying some. And would this make a difference? So every poet is happy, some programmers are wealthy, so that means some are wealthy, maybe some are not. And then no one is happy and wealthy. So can you draw the conclusion a person can be a poet and a programmer? Is that possible?
Yes. Because they could be a programmer that is not wealthy, which would allow them to be happy, which would therefore allow them to be a poet.
Right. Right, so you're just finding, based on the subsets of this, so again, they're separate, they're disjoint, but a person can be a poet and a programmer, so this would be true. Actually, such a program and such a programmer must be not wealthy. So you're either you're either, what do we say, this was happy and this was wealthy. So poets are in here, and programmers could be in here or outside of here.
It's the poets and the poor programmers.
Right, so poets and poor programmers. Right, so now, yeah, so just what sometimes in the artificial intelligence class is you start having rules which get converted into sets, and you need to populate every partition, like put at least one member here, one member here, one member here. If they overlap, put a member that's in the overlap. And then you just start querying, do I have at least one member in any section? And you can answer some of these true or false questions. If there's nobody in the section, that means it can't be true. And if there's someone in the section, then it could be true. Okay. Okay, and then there's the idea, so this is kind of a little debatable whether this falls under set theory or not, but the idea of sets, we could make a, you ever get these things on Facebook, like you see the pattern, like you see a number 1, 4, 9, and then you say, what's the next number? So, you could think of these numbers as a set. Like, suppose I gave you the set of 1, 4, 9, what's the next one, and so on.
16.
Yeah, that'd be 16. So maybe you could see each one is a square on an
Yes.
integer. Okay. So suppose somebody wanted to, so this really, it kind of overlaps, it's using a proof to prove something is true for all possible inputs. So where this comes up in computer science is, if you're asked to write an algorithm to solve a problem, let's say, you know, on your GPS, you have how do I get from point A to point B? And hopefully it tells you the smartest, the quickest way. There's many ways to go, but you want the quickest way. So suppose you came up with an algorithm that takes a bunch of, let's say, cities, and you have to hop from one to the other to get to a final city. And you want to know what's the quickest way, and you say, okay, I have an algorithm. And it works. It finds a path, right? But let's say you wanted to go from New Jersey to New York City, and your algorithm said, oh yeah, go down to Florida, go out to California, and then up to San Francisco, and then come back. That will get you to your destination, but it might not be the smartest way. What if somebody said, is your algorithm finding the path that is the most efficient? And you say, yeah, I think so. But you want to prove it is true for every possible map you could put on it. There's infinitely many maps for you, so it'd be hard for you to say yes, and for every possible input map, my algorithm will give the best answer. But you want to be able to show it, like, if it's true for one map, and then it was true for another map just like it, then it would be true for all incremental maps, something along that line. You'd like to show that something is true in every case without actually running every case, because there might be infinitely many cases. So, for example, this is called, so anyway, let's say we had a set X, such that X is the sum of consecutive odd integers starting at 1. So if we took, for example, this is our set, 1, 4, 9, and so on. And we're going to say 1 is equal to 1, 1 plus 3, the next consecutive integer, 1 plus 3 is 4, 1 plus 3 plus 5, added up equals 9, 1 plus 3 plus 5 plus 7 would be 16, and so on. So if I asked you, can you think of a formula that could generate the next one? Well, you might notice right away it looks like n squared, right? The number of integers squared. So suppose somebody came up and said, yeah, the first n odd integers sum to n squared. Is that true? We can see it's true for the first 3. To prove it's true in every case, we have to go off to infinity and show it's true in every case. Is there some way we could kind of make one big statement that says, yes, this is true in every case? One way, like I said, one way you can do it is just enumerate every possible one off to infinity, but you'll be doing that your whole life. Is there any way to just say something like, well, if it's true for 1...
Could you do like a sample size?
We'll just pick a number.
Pick like any, X amount of numbers and it...
Well, that would show it's true for that set of numbers.
Yeah.
But is there a way to say it will be true for all possible sets of numbers, and there's infinitely many of them. But anyway, so one way you could do it, I think, would be, well, does anyone have any intuition that that you can make the argument it will always be true. So here's kind of what, like, yeah, we have a theory. A theory is that the first n odd numbers will sum to n squared. Is that going to be true in every case, or does, like, after 1,000 it stops being true? Is there some way we can make the statement, this is true in every case?
Other than saying that it's true in every case?
And just hoping there's no exceptions? But, well, I get, no, what were you going to say?
Could you write like a law about odd numbers that kind of defines it so that it would have to be true? Like if the numbers are all odd. I don't know, I'm just
Well,
guessing.
yeah, I mean, so one kind of just kind of maybe intuitive observation might be, however many numbers you use, because you're always starting at 1, however many numbers you use, like 1, 3, 5, that's 3 numbers, and what would be the average of the 3 numbers? If there was an odd number of numbers, the average would be the middle number, right? Which is going to be the number of numbers. In any odd case, it would be the number of numbers. So any odd number of strings would be n numbers, all averaging n. So then you could say, okay, then that would be n times n on average, you know, the number of numbers times the average value. And what if there was an even number of numbers, like 2 and 4? Then the average of these 2 numbers would be the average of the 2 middle numbers, which would also be the number of numbers. So in other words, so if we had 4 numbers, like 1, 3, 5, 7, the average of those 4 numbers would be the average of the 3 and the 5. The average would be 4, and there'd be 4 numbers. So it ends up being the number of numbers times the average number would always be n times n, would always come out n squared. So that's kind of one observation. That's like an unofficial, you know, observation. But so we'll say, yeah, the number of numbers will always be n, and the average of the numbers will always be so that the sum adds up to n times the average of the numbers, which is n squared. So that's one observation. Maybe, you know, you're lucky enough to see that. But there's also a topic called proof by induction. When you want to prove something is true, a statement is true for all infinite possible inputs, and you don't have time, you don't have an infinite amount of time to do it. You could say, if the statement is true for one case, if it's true for one case, that doesn't mean it's true for every case, it's true for the first case. But if you could show that if it's true for n, then it must also be true for the next one, the one right after it. If that's true in every case, right? So if it was true for 12 numbers, it's true for 13. Then that would mean it's true for 14, and that would mean it's true for 15, and that would go off to infinity. So if you could prove both of these are true, then you have in fact proved it's true all the way off to infinity. So suppose we had numbers like 1, 3, plus blah, 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 and it went all the way up to 2 to the n minus 1. Suppose that was true in one case. Then the question is, what if we added one more number? Suppose we added n plus 1 to this side. The next number would be 2n plus 1. The next number we would add to this. What if we added 2n plus 1 to n squared? So in other words, if it was true in one case, if this is true for n, would it also be true for n plus 1, one more number? So if you took this whole string, 1, 3, 5, 7, 9, all the way up to some number, and then you went 1, 3, 5, 7, 9 plus one extra number, the next number, is that always going to be equal to whatever this was plus that additional number? And this, you remember from mathematics, is really n plus 1 squared. This is just another way of writing n plus 1 squared. So what you're showing here, so step 1, you're saying it's true in the first case. 1 is equal to 1 squared. That's true for when there's one digit. Now we're showing that for any number of digits, if it's true for any number, it's also true for the very next number. So what we're really saying with these two statements is, it's true for the case where there's one digit, And therefore, it's also true when there's 2 digits, and 3 digits, and 4 digits. If it's true for 4, it's true for 5. If it's true for 5, it's true for 6. If it's true for a million, it's true for 1,000,001, and so on. So this would be a way of proving that this would be true in every case. So when you're designing algorithms, in your algorithms class, you want to say, "Hey, I have a problem, here's my solution to it." You run it on one set of inputs, and it works great. But you also want to show it would work for every possible combination of inputs. And you don't have infinitely many time to input every possible combination, so you don't know will your algorithm will always work, or does it just work some of the time. So you'd also want to provide a proof, and it's usually done with proof by induction, that your algorithm will work on every set of inputs. So this is just kind of like a lead into that kind of thinking. So it kind of overlaps the topic of set theory, so it's kind of good to put this in at the end, because we could be generating sets, or you could be describing a set. You could be describing a set as these numbers, 1, 4, 9, ... And you want to know, maybe you're asking a question, is a number part of the set? And you want to know if we can use this formula. So you might ask yourself, is number 64 in this set? Well, one way to get there is to just keep generating the next number until you hit 64, or if we could come up with a formula and just say, oh yeah, that is part of the set or not part of the set. But you want to prove to yourself that it's true in every case. That's why this topic kind of overlaps with set theory.